Good morning. I will do a little bit of administrative stuff. All the homework is up on Pearson. I will have the last two exams. We're going to have there's due to be an exam on Chapter 4. I'm right about now-ish, but we kind of down a week with the extended break coming back out of spring break. And then there is the final exam, which is mostly Chapter 5. The nice thing about this type of material is I hope you can see that we're still doing things with functions. We still do things that we were doing in Chapter 1 linearly, as we did these higher order polynomials, and we still fall into quadratics as we break things down. The things that I introduced in Chapter 5 use the basis of what we've learned before, so I don't have to go back and pull a lot of information from previous chapters to make a quote-unquote cumulative final. Asking you questions on Chapter 4 and 5, or on Chapter 5, will have a cumulative effect, especially the sections on function algebra, which is what we start with. In fact, the stuff that finishes Chapter 4 really does straddle the line between Chapters 4 and 5, because we're going to do some algebra with polynomials. But that said, so all the homework is up. I'll put the exams up. All the exams will have a due date of May 10th. Grades are due the 13th, which means I need everything by the 12th. So I've been asking people, if you feel you need more time because of the change of circumstances, we need to have a discussion, because I have to do something called an incomplete, which means that we keep working on the stuff into the summer semester a little bit. And that holds up the grades. It shows as an incomplete in the grades. If you're transferring somewhere or you're graduating, an incomplete probably would not be the best thing for you. So this is a conversation we need to have. Look at where you're at and what you think you need to do. I will have both of those exams up this evening. I'm really doing this for all my classes, getting all the material out to the end of the semester up on Pearson so people can access it and use it as a reference. I would believe use the homework, the stuff we're doing right now, you don't get unless you play with. In fact, the stuff we're doing today is one of the things you're going to see. I hope it opens up well here. Let's see if it does. Yeah. That I go to my graphing utility a lot. And so I'll be using Desmos a lot to visualize some things, which is a good use for it. So you kind of need to get those visualizations in to get a hang for it. So that's the administrative stuff I have. Continue to email me questions. When I get questions, I will put up examples on the playlist coming across. I have yet to figure out. I would prefer, if this was a course where lectures are recorded, that the lectures be a little bit smaller. But the amount of material that we're covering in what would have been the time period of a class period, it's a weird trade-off. I have always found that a 2-class-a-day thing is a little bit too long for mathematics without kind of flipping the classroom. And so I advise use the lectures, kind of get your questions asked, and maybe go back and look at them in pieces. I'm hoping maybe someday to edit these down into smaller chunks as a reference point. But that's not an administrative for this class. It's more of a wonder of the format and how we manage time. All right, so the thing we're going to be talking about today, I guess I'll just do it, and we'll see what happens to it. And the reason I say we're going to start doing algebra with functions. All right, so this is where we're moving to, algebra of functions. And so I could take a function, f of x, and I could add it to another function. Or I could subtract a function from it. Whoops. Or I could multiply two functions. And divide. And then there's a weird thing we do where we make one function, the input of one function be the output of another function, which we'll end up calling a composition. So that's where we're going with this. This one here, though, can be a little special. And a lot of that has to do with the problem that we have where dividing by zero is not defined in mathematics. For how we define the operation of division, zero doesn't make sense. It doesn't give us a unique answer, or the concept of something being in zero parts doesn't have a definition. So we say dividing by zero is undefined. And we've done that in like finding domain restrictions and other things, where we've had to look at the restrictions it brings. So what we will define or talk about first is we're going to start with what are called rational functions. They're a subset of the idea of function division. They're not every possible division, but they're a certain set of divisions, so that we can get used to the idea. So this is where we're going. This is the first part of chapter 5. And one part of that division is rational functions, which is the last part of chapter 4 for us, the 4.6. So we're going to, look at rational functions. So I guess what we're going to have to do is we're going to have to define this thing. And so we're going to say that f is a rational function represented by, all right, we get all these lovely symbols in mathematics as ways of being shortcuts for everything we've done before. And so in this case, we're going to say a rational function f of x is some p of x over q of x. All right. I'm going to scroll this up so we just see rational functions now. Where p of x and q of x are polynomials. And the domain of x domain of f, sorry, are x values. The domain of f is restricted such that q of x cannot equal 0. So I wanted to get all that down, put it up on the board there, and kind of talk about what this is going to mean for us. So go back to our definition of a polynomial here. I don't think I'll do it in a limeish green. I'll just put poly here. With some function, I'll give it a big F to distinguish it from above, where we had these series of powers of x, and we would write them in descending powers so that we would know the degree of our function. But there were some things that had happened. N had to be greater than 0. Well, actually, we could have a constant, so we said greater than or equal to 0, and n had to exist within the integers, right? N was an integer. So it had to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Couldn't be 1/2, couldn't be 1/3, couldn't be -5. And that limited the things we could do, but the polynomials are fairly powerful things. And so we looked at that subset. In fact, one of the things we've kind of been doing is we've been slowly limiting the things we can see so that we see different parts of mathematics and develop some patterns underneath them. Oh, if all these exponents are integers, we get these things called polynomials. Well, what do they do? Well, we can find roots and solutions with them. Oh, that's good. Let's work on that. And now we're going to start scrolling our way back to some of the things that we have overlooked by doing polynomials. And the first thing we want to do is we want to divide. And so we do this division, kind of like when the Greeks were inventing their numbers. They invented not their numbers, right? When Greeks were recognizing the pattern in nature that we represent with numbers, they saw integers and they saw ratios, rational numbers, ratios. And so we've recognized polynomials. Now we're going to do ratios of polynomials or divisions of polynomials. So we can look at things that are or are not rational functions, and we can look at the domain restrictions. So this definition kind of gives us two things. That top and that bottom have to be a polynomial, and that denominator has values of x that can't be 0. Well, what's nice for us is we're going to find these domain restrictions such that q of x does not equal 0. Well, that's the roots. I'll actually say, how about I'll say these x values. These x values are the roots, the zeros of q of x. And so all that work we did for finding roots is going to come in handy because we can find domain restrictions with it. Right? That wasn't the full purpose of it. In fact, roots are solutions. They tend to be the best place to set up equations and find solutions are to use the roots of the zeros. But for us, in this particular thing, that solution set happens to be the place where q of x equals 0, and they will restrict our domain. So let's talk about some of these things and what they look like or what they can mean. So if I have a function, (2x minus 1 over x squared plus 1). And I want to go, well, what can I say about this? Well, I'll write it in the form p of x over q of x. So p of x is 2x minus 1, and q of x is x squared plus 1. Now, this isn't a step you end up doing, right? We rarely say p equals the top and q equals the bottom. We look at them. I'm just breaking them out so we have our labels on them right now. But I want to check this. Hey, this is a first degree polynomial. And this is a second degree polynomial. Definitely keeping track of the degrees of your top and bottom help. So this meets our definition of a rational function. So f of x is a rational function. Yay! And that means q of x cannot equal 0. So I'll take q of x, x plus 1, and I'll set it not equal to 0. Means x squared can't equal -1. Well, that's nice because there is no real number that I can square that makes -1. We don't have to worry about the imaginary numbers when we're doing our domain restrictions because we're drawing from real numbers. So there's no restriction, right? There's no value I can put into x squared that's real that will equal -1. So I can say that the domain of f of x is all real numbers. And what were the ways we had to write this? We could say x exists in all real numbers with no restrictions, or we could do the -infinity to +infinity notation, the interval notation, or the set notation. I'm happy, unfortunately, with the all real numbers, but we're going to have to do some entries on the book here, and I believe the books will start using both the set notation and the interval notation. I'm trying to keep the questions with interval notations, but some of the graphing questions are better. And so you will get a different domain format there, which is okay. It's probably good to get used to the vocabulary of the different ways of doing this. If you ever have a problem with a question, you ask me, right? You don't sit there in frustration. Send me an email and we can see what happens and we can fix things. But we've looked at this function. We've noticed the top's polynomial, the bottom's a polynomial, and the domain is all real numbers. There's no domain restrictions on it. So what I'm going to do here is I'm going to pop up to Desmos. And we're going to look at what this looks like. Now, I have to make a fraction out of this, so I type in my 2x minus 1, and I highlight the whole thing, and then I hit my division symbol. That'll put me down in the denominator. And then I'll do x squared plus 1. And there are some things that happen with these types of numbers, or with these types of functions. And so I'm going to put another thing here just to illustrate something. I can type properly today. There we go. And let me... So in Desmos, I put in the function I was looking at. In fact, I'll even be pedantic enough and I'll call it f of x equals. Right? Put it in green, and I put another line in here called y equals 0. And we'll talk about these extra lines I'm going to be putting in when I illustrate some things as we go on. But for right now, I just kind of want to look at this. So this function has some curvature to it. That's from the polynomial nature of the polynomial parts in it. But it has some curvature. All right, good. So I'm explaining. And if I scroll very far away from it, if I look at its big end behavior, it's getting close to 0. Right? If I get very far away from it, it gets to 0. So it has a big end behavior where this function tends towards 0. In fact, it's tending towards that line I drew, that blue line this function's trying to get close to. And this blue line is a line that the function gets close to but never touches. It never equals 0. Well, no, this can equal 0. It equals 0 here. Right here it equals 0. And then as it goes off towards infinity, it gets close to 0 again, but never quite touches it. And that idea of the line of the function approaching this line is going to be a new term we have. It's going to be called an asymptote. And in fact, you'll hear me talk a lot because it's a very important concept in mathematics, is asymptotic behavior. And so, I'm going to get us back on everything. You're going to hear me talk when I switch between screens, pausing a bit and double checking. And yesterday, for some reason, it kept switching back and forth. I think it was just the way I was clicking. It's an asymptote. So an asymptote is a line and a function approaches, but doesn't touch. There's different types of asymptotes, and most of what we're defining in this section are going to be the different types of asymptotes and how to find them. So I want to come back here to look at this graph again. So it's approaching the line of y equals 0. What we can say is as we get towards infinity, the ones don't matter, right? This one and this one. If I'm close to infinity, if this is 4,582, and I go to 4,583, if I subtracted 1 from that, and that was money for me, I wouldn't care about that one, right? Well, that's what functions do. Is they get really, really close to infinite amounts. Adding or subtracting 1 from infinity doesn't change anything. Its behavior is approaching this thing off towards infinity. And the same thing's happening here on the bottom. X squared plus 1, well, if I have something that's approaching infinity and I'm squaring it, and I'm adding 1 to it, I won't notice the effect of that 1. I always like you using money, because I can say if you gave me $1 billion and you squared it, would I care if you added 1 to that or not? No, right? Not even a cup of coffee. As I drink my cup of coffee. And so the constants fall away. Now the other thing that ends up happening here is that, well, if I have 1 billion upstairs and 1 billion squared downstairs, well, the bottom gets really, really big, right? 1 billion upstairs and 1 billion squared downstairs, that's like 1 divided by 1 billion. So as those x values go off towards infinity, that squared thing is getting bigger, faster and faster and faster. And so this bottom term is dividing this more and more quickly. Well, when we divide 1 by a really large number, we get closer and closer to 0. Because I'm dividing 1 into more and more parts. Each part gets smaller and smaller and smaller. We get closer to 0, but we never get there. And so that drives this asymptotic behavior, is I am dividing, and I'm getting my answer closer and closer and closer to 0 by this large number I'm dividing by. So my function gets closer and closer and closer to 0. If I could get to infinity, could I say it's 0? We'll need Newton to invent calculus, Newton and Leibniz to invent calculus to, I think, answer that question a little bit better. But at least we know as we're going towards infinity, that's what the behavior is doing. And so this type of asymptote, the y value, or the total value of the function, is approaching the value of this horizontal line. All right, so we added a definition. Let's look at another function. So go back to red for my function, and just realize that we're going to have these things called asymptotes, and we're going to define them. We have an idea of how they work, and we'll explore that idea more and more. All right, so we have g of x equals 1 over the square root of x. Oh, this is a valid function. And I'll look at it, I'll do this again just for illustrative purposes. P of x is a constant polynomial, and q of x has a square root in it. So P of x is a constant polynomial, while q of x is not a polynomial. And our definition, the thing that we're doing right now, wants us to have polynomials. And so with q of x not being a polynomial, g of x, almost went and did a q again. G of x is not a rational function. It's not going to be the definition of the things that we're doing right now. Though a lot of the behavior we're going to learn, we could map onto this, and we could learn some things about it. So we're going to look at it, but we won't use it like we did. All right, so let's look at the domain of this, because we still have this restriction that q of x cannot equal 0. Well, it's also a square root function, so q of x can't equal 0, and the square root of x has to be, implies that x itself has to be greater than or equal to 0. So when I apply these two rules together, if I can't equal 0, and I'm in here and I have to be greater than equal to 0, I'm going to lose that equality. And at the end of the day, my x has to be greater than 0. So I can say that my domain, x is an element of all real numbers such that x is greater than 0. Right? X is an element of all real numbers such that x is greater than 0, or it can't equal 0. Oh, I'm sorry, greater than 0, not greater than or equal to. Said the one thing. Words! X is the element of all real numbers such that x is greater than 0. So I'm at 0, but I can't equal it, and I go all the way up to infinity. Those are my two domain notations. Now again, the important thing is for the context of what we're doing, the asymptotic behavior we're looking at, the things we're going to do with this function algebra, we're not going to call this a rational function because it's not a polynomial downstairs. Not a rational function. But we can still talk about the domain and the domain restrictions, and I want to show you what this one looks like also. Oh. Yell at me. Yep, I got you, Billy. Sorry about that. Little bit of a delay here. I'm going to re-talk back. This is the problem I've been having with this. I click on the thing, and when I open the window, it bounces back a bit. I'll try to look at the chat window a little bit more. Sorry, Billy. Thank you for that. So I will repeat all those wonderful words that I said. So we had our asymptotic behavior. We defined asymptotic behavior as a line that a function approaches and doesn't touch. And that's what I showed on the graph. And I came down and I want to look at a second function. G of x is 1 over the square root of x. Now if I break this into its two polynomials, or the numerator and the denominator, the p of x is 1, which is a constant polynomial. The q of x is equal to the square root of x. This is the downstairs. And so we kind of want to think upstairs, downstairs. Right? And the q is for the quotient. P and q always seem to be the variable in fractions in mathematics. I've yet to find a good definition of why they picked p and q. I think product and quotient might have been the things that came about it, but it is really the divisor and the dividend. So it is what we have. Q of x is not a polynomial, right? This is a power, we could say this is a power of 1/2, and our polynomials needed these to be integers. So q of x is not a rational function. But we can still look at the domain restrictions. So q of x can't equal 0, and anything I put into the square root has to be greater than or equal to 0. These two rules combine. If I can't equal 0 and this has to be greater than or equal to 0, I lose that equal to part on this. And so my overall domain, x has to be greater than 0. So I'll write this in this notation. X is an element of all real numbers such that x is greater than 0. Or in interval notation, I start at 0 and I can't equal 0, so I get the parenthesis out to infinity. Sorry about the screen switching thing. I really want to get my second monitor set up so I can look at the chat window separate from the windows I'm writing on, because that also shows me what screen you guys are seeing. And I think this problem would go away a bit. I think it has to do with the way I switch windows. And it doesn't happen all the time. If it happened all the time, I could figure out the button clicker, the thing I'm doing to fix it. Thank you for putting that up there, Billy. I'm moving some things right now to make that bigger. All right, so we've looked at a function that was a rational function without any domain restrictions. We've looked at a function that isn't a rational function with domain restrictions, and I want to view this in the graph. So I'll put this up here. Okay, I've switched over to a graph. And it's switched over to a graph there. Good. All right. So I'm just going to turn these off. And I'm going to make this a g of x. And it's equal, and I'm going to do 1 divided by, I'm just going to type the sqrt, gives me a square root. If I need to pull a square root up in Desmos, it's in the keypad down here. And I'll put x in here. And so we have some behavior here. In fact, I will return on the y equals 0. And I'll put and so we do have some asymptotic behavior to this type of function. If I get really, really close to 0 for x, the smaller x goes, the larger my value goes. And so this shoots off towards infinity as x gets closer and closer to 0. As x gets larger and larger and larger, I'm dividing by bigger and bigger numbers, and so it also approaches 0. And that's going to be, I think, the overall thing that we'll see is when our denominators get bigger and bigger and bigger and bigger and bigger, we have this horizontal asymptote of the function approaching 0. And when our denominators get really, 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 really small, our function gets bigger towards infinity. All right, let's look at one more variation of what a rational function can be, and then we'll start pulling out our asymptotes. So we're going to look at h of x is x cubed minus 2x squared plus 1 all over x squared minus 3x plus 2. So my p of x, again, we don't really do this step, but I'm using it as a label. I won't even say it's a step, it's just a way of isolating things to view them. I tend to look at, hey, my numerator, oh, my denominator. Though I'll say, hey, my upstairs, hey, my downstairs. Yes, we did switch over. You should be seeing these. That's good. So this is a third degree polynomial. And this is a second degree polynomial. So we have a polynomial, h of x is a rational function. Meets our definition that we need to work with. Again, we're just limiting some things that aren't polynomials to define the space we're looking at. We will build the space up a little bit as we go through. Our goal right now is to look at this as, hey, I had two polynomials, I divided them by each other. Because we're going to do other mathematics with polynomials. This is a good idea to see how polynomials interact. All right, so q of x cannot equal 0. So x squared minus 3x plus 2 can't equal 0. Well, this is quadratic. And so the places where it would equal 0 are its roots. So what do I have? I have x minus 2 times x minus 1 can equal 0. Let's see, that gives me x squared minus 2x minus x, which adds up to the negative 3x. And the negative times the negative is positive. Yep, that works for me. So I have x minus 2 can't equal 0, and x minus 1 can't equal 0. Or x can't equal 2, and x can't equal 1. So my domain with these restrictions in place is x is the element of all, or is an element of all real numbers such that x doesn't equal 1 or 2. Or I can go from negative infinity to 1 without it equaling 1, from 1 to 2 without it equaling either of them, and from 2 to infinity. Right. This is where the top notation comes in, is a little bit neater. And so we have a rational function with a domain restriction. It can take all real values, except the function has no definition at 1 or 2. Well, let's see what that means, having no definition at 1 or 2. So I'm gonna, all right, so we'll definitely see that. So I'm gonna switch over to the graph. You guys should have the graph now. That's good. Come back over to my graph, and I'm going to put in, I'm going to turn off these, because I'm going to put in h of x is equal to, and my upstairs was x cubed, so x shift 6, 3, use the arrow to get off of that, minus 2x shift 6, 2, use the arrow to get off of that, plus 1. And so there's my polynomial. I'll highlight all of that and then hit my division, which is the slash, and I'll get x squared, shift 6, minus 3x plus 2. So some unique things happen here. So first off, this function has two distinct parts. There are two parts to this function. There's the side on this side and the side over here. Now, let's look at x equals 2. That was one of the places where this function couldn't exist. And we'll see that x equals 2 is one of our asymptotes. In fact, it's the defining part that divides this function into its two parts. Where the 0 is in this function, its denominator, what defines one of the asymptotes here, gives two distinct parts for this function. In one side, it's shooting downwards, and the other side, it's shooting upwards. We're shooting downwards here, and we're shooting upwards here. But the other divide by 0 portion does exist within the function. In fact, there's a point right there at 1, 1. Now, what is it? It's more like 1. Let's see, let's get on this one. Yeah, 1, 1.